looks like we can get going. Welcome, everyone. I hope you had an enjoyable evening, went to the party and had a few nice beers and maybe a little bit of dancing. And anybody gamble at those tables? I assume it was just fun gambling, but looked pretty interesting. All right, so today I'm going to talk a little bit about how we can call down to native libraries, native code, do things that were considered evil to past generations of Java developers, but are becoming more and more important. Basic info about me. I'm hideous on pretty much every service, so should be pretty easy to find me if you want to hunt me down. And I have been working for the past 10 years on a project called JRuby. JRuby is a Ruby that runs on top of the JVM. And you can imagine that a language that comes from off the platform, a language that was never designed for the JVM, will have various issues, various challenges to try and make it work. First of all, of course, JRuby is a dynamic language, which means we have to use all the best tricks and all the best new JVM features like invoke dynamic to get things to run well. We actually had to implement our own string logic. So we have our own string implementation that can support many different encodings at the same time, our own regular expression engine, our own I/O subsystem, lots of things that we had to build to basically mimic how the C implementation of Ruby handles strings and native I/O and so on. We've had lots of challenges with the startup time, and honestly, if we didn't have problems getting started and getting going quickly, we'd probably be the sole Ruby game in town. It's the only thing that really is a problem with JRuby at this point. And what I'm going to be talking about today, we have had to build a lot of support for calling native libraries, integrating with standard POSIX function calls, and so on. And we have done that as a standard standalone Java library that you all can use as well. So what sort of things do we have to use native calls for in JRuby? Why do we have to go around the JVM or use native functions at all? Well, there's a few things. The big ones that we had to deal with initially is operating system level features that were not supported in any version of Java. File system metadata, for example, which is only even now partially supported in ENXIO 2 that came along with Java 7. Various ways of spawning subprocesses with full control over them. Anybody who's tried to do interactive subprocesses on the JVM with Process Builder knows how poor the API is and how difficult it is to make that work. Being able to stat files, being able to manage TTYs and PTYs and so on. Lots of the things that C developers on Unix take for granted, we basically needed to be able to do. And there was just no way to do it using standard Java APIs. There's lots of other libraries out there that Ruby developers expect to be able to access, graphics libraries, crypto libraries, and so on. In fact, the standard Ruby library for accessing the 0MQ system is actually written in some of these libraries that I'll show you today. It works on both JRuby and CRuby, but it's using sort of a reflective way of calling down to native code. CRuby also had a lot of C extensions. The typical way that you got around performance problems in CRuby was to write it in C and load it back in as a dynamic library. We needed a way to replace those. In a lot of cases, those wrappers were simply just wrapping some other C library. Being able to do that from on top of the JVM makes it possible for us to avoid the C extension issues. And then, of course, there's lots of other languages and runtimes and things that people want to be able to call out to on a Unix system. Simple enough to do in C and just write some code, but on the JVM, we had to build some tricks. So let's talk about a simple case. How do you get the PID, the process ID, of the current process on the JVM? Well, it turns out that there is no good way to do it through standard Java APIs. The best way that I've found is that there is a java.lang.management call that you can make that will give you a string that represents the system you're on, and if you parse part of that string, there is the current process's PID embedded in there. That's about as close as you can get to being able to do a simple get PID call on the JVM. But get PID is a very simple function. We should be able to just call something like this from the JVM to get the current process ID. Right now, not an easy way to do it except through our libraries, and that's what I'll be talking about today. So the typical way you'd do this, if you wanted to call some piece of C code, a library or standard POSIX function, would be to use JNI. So let's walk through JNI a little bit. So JNI was first standardized around Java 1.1. Really has not had a whole lot of changes since then. There have been a few additional APIs here and there, a few things that have been deprecated, but largely the JNI API has not changed a whole lot during that time. And they say it was designed to be hard to use. To that, I say mission accomplished. It's incredibly hard to use. No one really ever wants, is there anybody that loves writing JNI code? No, of course not. No one loves this code. So let's walk through how you actually use JNI, the standard way that you have to follow to call native code today. All right, so we've got our user code, we've got our JNI stuff, and we've got some target library. Let's figure out how to do this. So anybody who gets into doing JNI and says, okay, I want to actually call a native library, well, okay, this doesn't look too bad. So we create a function prototype here, we throw this native on it, and then we can call it. It's like magic, right? We've got our native call, no problem, we're calling getPid. Oh, but I can't just call getPid. I can't just tell the JVM, there's this C function out there I want to call. No, okay, so how do we do that? We can put this native on here, we've got our getPid. Oh, but we need to actually load the library that it's going to be in. Well, and in this case, it needs to actually be coming from a JNI specific dynamic library. So okay, let's continue on this process. I need to call getPid. I got to find a way to do it. So I'll use the Java H command, which very few people know because nobody ever wants to do this. So Java H will generate some code for us. And oh, the horror! Now we actually get into C, and we see the violence inherent in the system here. Okay, so this is messy, and we've got these nasty naming conventions that are used to wire up some C function to our native Java function. Pretty horrible so far, but we can deal with this. This is generated code. Java H also generates a little stub for us, which again has this long mangled name to represent our package, class, and function that we want to bind. And it has some arcane JNI parameters here, some environment that presumably represents the state of the JVM, a J class, which I guess because we're calling it a static function here, this is basically the class object we called it on, right? And then we finally have our actual call to the C getPid function. All right, so this isn't too bad. Now we've got our code, we've got our header file, we've got our C code. Oh, but I can't just ship this in a jar. Even if I just build it, I can't just throw this library into a jar. So let's take a look at building it first. So here's the arcane command line on just one system to get this one library to build. And of course, this is also something I'd never wanted to have to deal with, to be able to just call a simple C function. And then it just gets worse from there. So most platforms have their own custom specific tool chain that you're supposed to use. So there's the mystery and magic of auto tools and configure. There's various different variants of make. There's an entire other set of tools that you have to use if you're building on Windows. And so you can write this stuff, and you essentially have to write the code and then struggle to get it to build everywhere. Or you can ship binaries, but then you need to make sure you have binaries for every platform, and you can't run those from within the jar file. So you have to do extra logic to actually unpack a dynamic library somewhere safe, load that dynamic library, clean it up after you're done, and ideally not introduce any major security issues into your system at the same time. Okay. We're Java developers. We don't want to have to deal with any of this stuff. All I want to do is call a simple C function. And the truth is that working with C, working in the native world, requires a completely different skill set than what we're used to in the Java world. We're not C hackers. We're certainly not make hackers. How many people have ever edited a make file? All right. It was a lot of fun, right? Yeah. There's a couple people that actually like it, but few and far between for sure. And then of course building shared libraries across platforms. We're Java developers. We write it, we build it, we ship it as a jar file. We don't have to rebuild it on every single platform. And just because we want to call a function that basically exists on every platform in existence, we shouldn't have to do this. And then, of course, the problems with JNI just go on from there. JNI, as the API, is very big, very arcane, lots of ways to make mistakes, accidentally root objects in memory, cause leaks, cause memory leaks in the C world. So many reasons why we just want to avoid this. So we need to get past this, because we do need this. We need this more and more every day to be able to call stuff. So for example, as Java developers, we had to wait for NIO and NIO.2 to come around as standard Java APIs just to be able to work with native I/O or to be able to deal with file system metadata that wasn't available on the JVM. We shouldn't have to wait for that. If there's functions out there that give us operating system level features, we should be able to call them. Unmanaged memory, lots of different databases and libraries and high-performance systems now are moving more of their memory off heap, dealing with it outside the JVM heap so that they're not influencing the garbage collector and dealing with the problems that come along with that. We need a better way to do this without having to use tricks like unsafe or ugly hacks around byte buffer. Anybody, like I mentioned, has done sub-process I/O or has dealt with console I/O from the standard I/O. You can't get any actual selectable channels. You can't actually get channels for any of this. So you can't do all the NIO things like doing a select loop to see if any input's been submitted. Managing a sub-process interactively. This is all pumped into streams behind the scenes with multiple layers of buffering. Very difficult to actually work with the native I/O file descriptors. And then, of course, other types of sockets. Unix sockets don't have any good way of being used on the JVM right now. Different types of sockets that we can't create through standard JVM means. And then again, back to all those APIs like graphics and crypto and so on. So there's lots of stuff out there that we should be able to use on the JVM without going through all the pain of writing JNI. All right, so what's the real problem here with this system? Well, the problem here is that I have to implement all of this. I have to implement all the pieces in purple here just to make a simple C function call. And I say that there's got to be a better way. There needs to be a better way on the JVM. And the way we've approached this is by building something called the Java Native Runtime. There's a GitHub URL if you want to go to the organization. Number of projects under there to make it a little easier for you to call native code. So the Java Native Runtime is a Java API, standard jar, standard library you can ship, you can link to it in Maven or whatever, for calling out to native code. And on top of this, we've built a set of runtime libraries, rich libraries of pre-bound functions and utilities that will make it easier for you to integrate with native libraries. Some of you may be familiar with the Java Native Access library, which does at least a small part of what JNR does. I'll talk a little bit more about our comparison with JNA later. And again, there's the URL for it. So basically, this is a Java API for binding native libraries and native memory and managing them. Calling functions, getting results back, dealing with native memories and structs, just like you would in C without writing any JNI code. So the way we do this in JNR as compared to JNI, all you really have to write is that piece at the top. You define the functions that you want to call, you define the memory structures you want to deal with, and then you tell JNR, go forth and make these calls for me. Do these native interactions for me. And this is significantly better. So here is the entirety of our getPid example in JNR. Standard Java code. We'll walk through it a little bit here. So we define an interface. In this case, our getPid interface just defines one function that on pretty much every platform returns a long value. We have our code down here that says, JNR POSIX library manager, please create an instance of this stub and bind it to the library known as C, the C library, libc, glibc, whatever it is on the platform. And that's it. We call getPid, and we're ready to go. Pretty nice. Significantly better than JNI. Nobody that's ever done JNI would ever think of going back after seeing what we can do with JNR. Okay, so I mentioned a layered runtime. I'll go through various pieces of this, but we have lots of different utilities, things that we've found useful in JRuby or needed to build for JRuby that are, again, just standard Java libraries for everybody else to use now. So at the bottom, slightly above the native libFFI that we use to bind functions is JFFI. This is Java Foreign Function Interface. You'll see FFI come up a lot in discussions about native integration, native calls on the JVM. That's what we're talking about, is Foreign Function Interface. I mentioned it's based on libFFI, which is a C library that's been around for decades. This is the low-level API. This is not really the one that you're looking for. This is where we do the actual binding of native memory, native functions, and do the low-level call. But it's where we provide all of our broad platform support. We have very few JNI endpoints that we've implemented here. We've got all the logic of unpacking the right library into a safe place, loading it up into memory, making sure it's cleaned up, and giving you access to native code without having to write any C yourself. So there's the URL for it. We're always looking for contributions as far as different platforms or improvements in the API itself. Here's I think a complete list of the platforms we support. Actually, ARM64 should be on there under Linux, but otherwise this is pretty complete. If there's a platform that you need support for that's not on this list, first of all, congratulations, and second, let us know and we'll work with you to get a library into JFFI so that we can support it. Kind of impressive that we actually have OpenVMS and AS400 support. Any OpenVMS developers here? Yes. Currently? No, I would hope not. We do actually have some people on OpenVMS that use JRuby. It's impressive that they're keeping the dream alive. So some bottom line features here for JFFI. There's no need for you to build anything other than your Java code. We've got all the libraries available. We handle the unpacking. The native footprint is fairly small. The libraries that we ship are only a few kilobytes in size. And basically punches a hole through that JVM into libFFI so that we can call these functions. So let's move on from this, because this is not the API you would normally use, even though it supports the whole JNR subsystem. So JNR FFI. JNR FFI is the user-oriented API that you'll be using if you start dealing with a lot of this stuff. This is roughly equivalent to what you get in JNA. That's essentially the example I showed before, where we've got our function that we've defined, we tell it to bind it, and then we can call into it. Functions, structs, we can actually do callbacks. You can say, here is a Java interface, an implementation of a Java interface. Pass this out to C as though it were a function pointer, and we handle the management of that function pointer on the other side, make it available to the C function so they can call back up into Java. And then, of course, just raw native memory access in various ways. There's the URL if you want to go grab it. There's also a separate project. The JNR FFI project itself is kind of light on documentation, I would say. So we have a separate project of JNR FFI examples that goes through a lot of common use cases. And then again, the example I showed earlier, this is actually JNR FFI code we're using here to do our get PID. A little bit more advanced example, say we want to call get time of day to get the system's representation of what the current time is. Or perhaps we need a higher resolution clock than we can normally get on the JVM. So we define our get time of day. It's going to return an int result code, as many C functions do. The annotations here indicate that this time val struct that we're passing in is, first of all, an out parameter. So we're intending to call a C function to fill in the blanks of this structure and then get the values out. It's transient, so after this call is done, no pointers need to be managed, no memory needs to be saved on the other side of the call, so we can throw that structure away. And then in this case, we're not using the pointer for the time zone information in get time of day. Here is our timeval struct. So timeval extends the JNR FFI struct class. We have a few of the standard platform types built in, like time t here. Signed long for things that are too wide or unusual on the JVM. We have representations of those. And then a simple constructor that says, okay, call the super struct constructor with the current JNR runtime. And then the rest is pretty straightforward. We create our little libc library that's going to call get time of day. We bind it to libc. We create a new timeval struct, call get time of day, and we can get the actual time of day struct information out of that. Pretty simple. Less code in many cases than you would actually have to write in C. You'd get the function prototype and you'd get the struct definition itself, but for the most part, it's basically the same as what you'd have in C without having any of the hassle of JNI. Okay, we'll go through some of the support libraries here. So the first one, if you're dealing with any typical C API, you're going to need to be able to use preprocessor constants, the constants that are defined for I/O and for sockets and so on. So yes, this is all the preprocessor constants defines that are in the code. JNR constants comes with a set of generation tools. So on any given platform, you can run a piece of code that pulls in all of those constants, generates some standard Java enums for them, and then allows you to use those constant values in your C calls. We've also built in a whole bunch of standard libc constant sets so that you don't have to deal with them. A perfect example would be if you want to use the native socket API to create various types of custom sockets that we can't do on the JVM. And all of these are defined as a set of a set of preprocessor constants in C somewhere on the system that you need to be able to pull in and pass to this function. For example, the domain, different types of socket domains, Unix sockets, internet sockets, INET6, IP6 sockets, and so on. The type of socket, is it streaming? Is it a datagram socket? Is it a raw socket? These sorts of things we provide because we figure lots and lots of people are going to need them. This is the current set of constants that we provide as part of JNR constants. Lots of standard ones. If you've ever done any C programming, you'll be familiar with these. So here is, for example, the sock types, where we've got our socket stream, our socket datagram. This is just a standard enum that you'll deal with, just like any other Java API. Behind the scenes, we bind that to a separate set of enums that map the local values. So whatever it is on Linux, we've got the actual constant values here. And this is what gets generated as part of our tools. So any set of constants that you want to be able to load into the JVM and have match the platform you're on, you can run these tools and generate the back-end code for it. A couple other examples. Erno, very important if you're doing C function calls and want to figure out why something failed. We have all of the standard Erno values defined, and you can go back and forth using the Erno enum or the actual code from C. Open flag, so if you're opening files with various modes and whatnot, many of these that aren't provided in any of the Java APIs. Shared locking, exclusive locking, and so on, being able to do that on create. Not shown here, but being able to open files on Windows as binary versus text, so that new line processing is not done. And a whole bunch of other constants that you'll be able to use. So any C library that's out there that uses constants like this, we probably have it predefined, and if not, it's easy for us to generate and include in the library. All right, so getting on to a little bit more functional stuff here, JNR POSIX. So this is a pre-bound set of standard POSIX functions. The standard C functions that you might have used at university or that you've played with whenever you've done some C development. We've got most of them bound here. If there's one that you need is not available, we can add it very simply. This has mostly been driven by what we needed in JRuby, and also Jython has helped contribute to this project. So things like process management, low-level I/O, file system operations, and so on, we already have bound into JNR POSIX so that you can just pull in this library and start calling them directly. The goal here is that ideally 100% of the POSIX API set that generally works across all platforms will be part of this library. So most of the functions that you will want to call on a standard C-level basis, we should have available at some point in the future. We're looking for help on doing that. As a bonus, we've also included a partial pure Java backend that tries to emulate as much of this as possible. Naturally, there's a lot of things that we can't do, like interactive subprocesses and so on. In those cases, you can either get an error code or an exception raised, depending on how you want that library to react. This is a short subset of functions that we provide in the library. Notable ones here, for example, getPID is already bound up there. Get the parent PID also, which is basically impossible to do from standard Java APIs. What else is fun here? Fork is provided and does not work because forking the JVM does all sorts of horrible things to it. Exec, so you can actually replace the current process and not leave one lingering around. Getting process times, so you can actually see CPU time and so on. All of these things are already available. So you throw JNR POSIX into your Maven project or your Gradle project or whatever, and you'll have them available. Down at the bottom is probably one of the most useful ones, POSIX Spawn, which I'll talk about a little bit later. It gives us great access to low-level native process management. A simple usage example from JRuby, you can pass in your own POSIX handler. So this is basically how you decide, does an error simply return an error code, or does it raise an exception more in the Java style? A few other things about how you want to manage the current directory, given that there's lots of applications running on a given JVM. You can pass in whether you want to get the native version or the pure Java version. In this case, JRuby has it configurable, so you can turn native support off if you are on a platform that it doesn't support or you don't want to deal with it. And then we have a wait PID call. So we've got some process ID. We call wait PID to get to wait for that process to terminate. If something went bad, we've got our errno enum values, our errno constants from JNR constant, so we can get the actual error code and what it means. So pretty simple. Again, throw it into Maven, you've got access to a whole bunch of POSIX functions without writing any C code at all. So on top of JNR FFI and JNR POSIX, we've built a few more libraries. The first is JNR ENXIO, and this is Extended Native Cross-Platform I/O. So it's sort of like NIO, the new I/O APIs, but better, more in tune with the way the native system works. It's an NIO-compatible library, so you get standard channels and standard operations that you would expect from NIO, but we're working with raw file descriptors here. So you can open a native file, stick it into an NIO channel using ENXIO, and work with it as though it was just another NIO library, and just another NIO channel call. Standard byte buffers and everything all work the way that you expect them to. But you also have low-level control over these file descriptors. So you can do things with them that NIO hides from you, makes it more difficult. Get information about the file descriptors, select on things that you normally couldn't, like standard I/O or processes, for example. There is the GitHub URL for that one. And the main channel that's interesting in ENXIO is native socket channel and native device channel. I'm showing native socket channel here. And really all you need to do, if you've got a file descriptor in hand, is construct a new instance of it. We give you a fully selectable, fully interruptible NIO channel that wraps that file descriptor and uses all native operations to do its calls and polling and so on. On top of ENXIO, we've built a JNR Unix socket library. And this is exactly what it sounds like. This is a Unix socket library that works within the parameters of NIO. It gives you a standard channel that you can use for Unix sockets. Again, built on top of JNR ENXIO, but it gives you a real Unix socket that's selectable and has all the NIO features. You just pull it into your project with Maven or whatever, link it in, and you can create Unix sockets and call into them. GitHub information for that one. Very simple example here. We've got some path to a Unix socket. You might imagine that this might be a MySQL or PostgreSQL Unix socket file somewhere on the system. Many administrators will balk at the idea of opening up TCP channels. On the JVM, that's what we have to do to get access to these libraries, or to get access to these databases, but not anymore. We can actually use Unix sockets and call into them directly. Things like doing socket pairs, if you want to do communications between two different processes, two different applications over a Unix socket. Again, all works pretty much the same, and this is just a thin layer on top of ENXIO. We're getting a pair of file descriptors, we're stuffing them into Unix channels, Unix socket channels, and calling back and forth. So I mentioned a couple times the problems of doing process management, and that was a common enough issue for us that we also built a library on top of JNR for doing that. So JNR Process is essentially a Java-Lang process or process builder look-alike. It's the same API that you use if you use Java-Lang process, but it's built atop ENXIO, JNR POSIX, all of the native bits that we've worked with. And as a result, you get real interactive subprocesses. You get channels that you can select on. You get to do actual direct native I/O to and from subprocesses, which is largely impossible using standard JVM APIs right now. URL for that. And again, these are all in Maven, so you can pull this in and have good subprocess support without having to write any extra C code yourself. The simple example, again, looks pretty much just like Java Lang process, but the magic behind this is that in addition to getting input streams and output streams, you can also get the actual input and output I/O channels, the real native channels, the real descriptors that go with the input and output, so you can manage that process and drive it interactively from Java without dealing with all the buffering and pumping streams and making sure that things continue to run. Internally, this is actually using all the standard POSIX calls that we've bound before. So we create 3 different pipes for our input, output, and error streams. We call POSIX spawn, and we've got access to the subprocess, exactly like we would if we were writing it in C. So I've mentioned JNA, and I said I was going to come back to this. A lot of folks wonder, why don't we just build on top of JNA? And initially we did. We started using JNA because it was available and it was the standard way that you would do this sort of calling on the JVM. But it turned out that it wasn't really low level enough for us to build all of our other APIs on top of. It had no built-in support for preprocessor constants. So we would have had to build the JNR constants functionality ourselves and then deal with it across platforms and so on. It didn't have any standard API sets. We actually started out with JNR POSIX as JNA POSIX, just because being able to call these libraries was not enough. We needed more support, more runtime libraries around it. At the time, it didn't support C callbacks. I'm not sure if it does now, but at the time, there was no way for us to call out to C and pass it a Java object or a function to call back up into the JVM. And then performance was significantly worse than we wanted. We needed something that was going to be much faster, more raw, routing around some of the JNI overhead. It was pretty clear that we needed a better implementation. And I will talk for a little bit here about performance, because this is one that definitely comes up when you're switching from JNI to writing stuff on top of the JVM. So we worked very hard. Me and the other folks that have worked on JNR have tried really hard to make this as fast as possible. We generate the stub behind the scenes. So there's not a lot of abstraction, not a lot of reflection, not a lot of magic behind that interface. We generate a single piece of code that goes directly into the native call. If you're running on JRuby, we actually bind this with invoke dynamic. So a Ruby function call that's going down to a native library in JRuby will basically have one hop to the native call and one more hop to get to the C function that you're actually calling. About as short a pipeline as we can get it. We also generate on the C side, we generate the JNI stub. So instead of reflectively calling these functions every time, using libffi, for example, to constantly, please call this function for me, we generate a little bit of JNI code at runtime, load it into memory, here's our JNI endpoint for this function, and it goes much faster and avoids a lot of the overhead of JNI itself. And like I mentioned, best case, probably about 2 or 3 hops from your call of a JNR interface, a JNR stub, to the actual C function that you're integrating with. Certainly less than using JNA, and pretty much the equivalent to what you would do writing JNI C code by hand. A little sidebar here, the magic that's behind the JNI stubs. Yet another JNR library we've built that you can play with if you want, JNR x86 assembly. So this is basically a little DSL and library for writing x86 or x86-64 assembly code, generating that into a native library, and binding it back into the JVM so you can call it. This is what we use to create our little JNI endpoints, so we don't have to write any additional C code for it. I mentioned it's used by JNR FFI and JFFI internally. And there's the URL. Anybody who's really wanted to write assembly code on the JVM, now you have a way. So let's look at the performance. This is a graph comparing our performance with JNA for a simple get PID call. And it works out to roughly 10 times faster using JNR. I know JNA's made some improvements in recent years. There's ways you can mark it up and say, okay, I want it to skip some of the additional processing it's doing. But in general, JNR should be faster than JNA, and oftentimes by quite a bit. We also have some annotations that you can pass in to speed this up. Normally, when you call down to a C function in JNR FFI, we save off on a per thread basis whatever the last error code was. In case you want to be able to go get it, we've got it preserved. It's not going to be stepped on by other threads. And so we saved that for you, so you can go get the error code that came out of it. If you're not interested in that, for example, if you're calling a trivial function like getPid, which is expected to always succeed, you can tell JNR FFI, I'm not really interested in those error codes. Don't bother with the extra overhead of preserving it. And that gives us about a 25% improvement, again, over just doing the straight up call with the error code preserving. Now, this isn't as good as we'd like it. If we compare this with, so here we go from the top, we've got JNR with the error code preservation. The green circles there are JNR if we turn off the error code logic. Actually, no, the green circles there are JNI. So this shows how our stubs in our generated code can, in some cases, actually be faster than writing JNI code by hand. And I'm not actually even sure what the magic is that's happening here. Perhaps the C compiler was not compiled with the best options, but we're at least on par with JNI if you tweak things a little bit. But the problem is those red X's along the bottom. So that's GCC optimized version of the little getPid benchmark that I created. And we have more work to do here. The real problem here is that when we get down to the nitty-gritty, when we get down to the assembly code that the JVM produces for our Java code, we've got this chunk at the bottom here. So instead of being able to say, OK, I want my Java code to actually call this C function, we have to call out to some interface, call through a bunch of JNI logic. The JVM has to make sure the JVM's in a good state. It's got to manage this stuff for us. What we'd really like to see, instead of doing the call to some JVM internal function, we'd like to see in the assembly code the actual getPid call. We'd like to be able to say, I want to call getPid from this piece of Java code. When you JIT it, just call that C function directly for me. And for that, we need JVM Help. So we need a standard FFI API in the JVM, and I've been pushing on this for several years, trying to get JVM folks interested. We need the JIT to be smarter about this. JNI imposes a huge overhead regardless of whether you need it or not, just to be able to call out of the JVM. Even for trivial functions like getPid, it has to make sure that the heap is in a particular state, make sure that the GC is in a particular state, manage the crossing of that boundary very carefully for you. In many cases, you don't need that. So there needs to be a better way of binding simple native calls to Java calls without having this extra overhead. And then, of course, if we have JVM help, we'll have possibility for introducing better security policies for calling native code, protection against seg faults, protection against accessing invalid memory, a whole bunch of features that could come along with the JVM being smarter about native calls. And the good news is that this is coming. So a few years ago, I proposed JSR 191, which is now called Project Panama. And this is actually JEP 191. So it was a JEP, JDK enhancement proposal that will eventually become a JSR. And this is in progress. There's work already done on basically building what is essentially an FFI API standard in Java. Parts of this may be in Java 9 hidden behind the scenes, but lots of folks at Oracle, lots of folks at other JVM organizations, for example, Vladimir at Oracle has been working on this heavily, are very interested in this, not only because they see the value of having a standard FFI on the JVM, but they don't want to write JNI either. And they would love to have something that lets them route around this and be able to write just Java code for doing all these calls. So keep an eye on this. Hopefully around Java 10 timeframe, we might be able to actually do a JSR and have a standard FFI that's built into Java. Until then, you can use JNR, and I'm open for questions. Thanks very much. So, who wants to call native code? Yeah. You're all just blown away by how cool it is. Or you're recovering from the party last night. There's a question up there.
Hi. My question is how you exactly manage memory. Is it close to unsafe or is it managed on the C side of the code?
Right. So how do we manage memory using unsafe or whatnot? I don't believe we actually use unsafe in any of our code in JNR. There may be a few small places we use it, but the fact that we can bind C functions means we can simply call malloc and free if we want to. And then we map that behind the scenes to something that represents a Java object, a Java struct. Because we have our own JNI library, we don't have to use tricks like unsafe. We don't have to hide things behind byte buffers. We can actually just allocate the memory. And you can allocate the memory too. Like you can use our struct logic, or you can just say, malloc, give me 64 bytes of native memory to use for this call. It's really up to you.
Hey. I have a question. If I want to integrate my own dynamic library, as I understand, all is only with already existed libraries.
So if you have your own library that you want to pull in, it's as simple as that getPid example. For simple functions, you just write your own prototypes for them in an interface, tell JNR to load the stub, and pull the library in. There's also a project, a third-party project that we're probably going to adopt called JNR Clang, or JNR CLang, however you want to pronounce it, which basically binds the libclang library from the LLVM project to generate a JNR FFI stub for you. So you can either do it by hand or you can use some of the generation tools. But any custom library of your own, you can pull it in and call it from Java. Nobody's going to ask about C++? All right, so while he's making his, what? 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 That's overrated. C++, overrated, I agree. And now it's...
So my question is, you have shown us some examples how to call a single C function. What if I'd like to run like a small C snippet?
So if you have a small snippet of C code that you want to run, that we do not have. There's no way you can do that right now. There's a possibility through something like JNR Clang, binding the CLang, libclang stuff, that you could basically say, here's my C code, compile it with Clang, and give me the library or native code that results, and then we'll pull it in. But it's work that we haven't done yet on that. That's one of the reasons that we built JNR Constants, because typically the C code that you want to write is going to be something like pulling in some predefined constants, predefined structs. The JNR Clang stuff can help you generate at least the equivalent binding in JNR FFI. Anything else? All right, thank you. Have a good day.